We all pray that this situation will never happen, that it will never be true. But if the United States were suddenly attacked, we must be able to retaliate quickly, precisely, and reliably, even in a densely active nuclear environment. The Minuteman weapon system is our primary retaliatory strength in the event of enemy attack. Minuteman can survive all the effects of a near miss by enemy nuclear bombs and still retaliate. Minuteman is dispersed far enough apart to prevent annihilation of more than one site by any single enemy bomb. Minuteman is a major part of our deterrent force, ready to do its job. If Minuteman is to continue as a successful deterrent force, we and the enemy must know it will survive, no matter what nuclear attacks are used against it. Protecting Minuteman with all its systems and subsystems is called hardening, and is the complex job of the Vulnerability and Hardness Division of the Space and Missile Systems Organization. Hardness, survivability, shielding, protecting, whatever the words, it is the survival of the Minuteman weapon system and the preservation of our nation that we are all working to accomplish. And survivability of the Minuteman weapon system is a continuous, meticulous, demanding job. The Minuteman missile and all its supporting systems must overcome 6 major nuclear components associated with the nuclear environment to enable a successful launch. These 6 components are always present in every ground burst nuclear explosion. Nuclear radiation, electromagnetic pulse or EMP, thermal environment, air blast, ground motion, and cratering and debris. Well, let's see what is being done to prevent the damaging effects of these 6 components on Minuteman. A nuclear warhead could enter here, close to a Minuteman launcher. During the initial explosion, about 3% of the total energy may be nuclear radiation, composed of gamma rays and neutrons. Gamma rays and neutrons in nuclear radiation are among the first components to be overcome in the nuclear environment. The question then is, what hardening methods protect Minuteman from these damaging effects? First, a 50-inch thick concrete launcher closure covers the upgraded launch facility. The Launch Control Center and the Launch Control Equipment Building are buried, usually 40 feet underground. The Launch Control Center has an access door of steel and concrete 2 feet thick. The access tunnel has 2 subsurface 90-degree turns. The Launch Control Equipment Building door is a shield that attenuates radiation. Ducts and vents are designed to prevent straight-line leakage of radiation, and the Minuteman equipment is designed to tolerate remaining radiation. Electromagnetic pulse, or EMP, is another major component in a nuclear explosion. EMP is a complex technological phenomenon. What hardening processes protect Minuteman from these damaging effects? A solid quarter-inch steel liner, electrical bonding and magnetic shielding at doors and all other openings, electrical surge arresters on entering wires, shielded compartment for electrical surge arrestor cable entries. All conductors enter the launch facility near the grounding point. All entering wires are shielded and filtered to prevent radiation. And the inside equipment is designed to survive the effects of the reduced EMP transients. From within one tiny bomb casing, temperatures of millions of degrees centigrade and pressures of millions of atmospheres are generated, resulting in intense thermal environment. The air is heated at a fantastic rate of speed. Materials on the ground are either vaporized or their exposed surfaces melted. The high turbulence continually scours away the molten materials, exposing fresh surfaces to the hot gases and their violent destructiveness. If weapon systems are exposed to this thermal environment, some surface materials can become welded together. Also, any leakage of high-temperature fireball gases through cracks or penetrations in the facilities can be very damaging. How then is the Minuteman weapon system hardened against the effects of a nuclear thermal environment? In two important ways. An ablation layer of steel or concrete covers exposed launcher surfaces, and blast valves shut and block off the shock wave. The Minuteman weapon system must also survive air blasts within the nuclear environment. The destructive force and effect of severe air blast on weapon systems can be instant and permanent. Now, what hardening methods have been devised to protect Minuteman from these effects? Launch facilities are designed and built to survive the pressure loads. The launcher closure is locked in place. Doors, locks, seals, pipes, and conduits are designed to limit transfer of acoustic shock waves. Air ducts are blocked by blast valves. Minuteman must also survive violent ground motion. A surface nuclear explosion deposits a great deal of energy into the ground. This compression shock wave of energy moves swiftly. What are Minuteman's defenses against these problems? Minuteman facilities are buried to limit ground shock loads. Launch personnel work on a shock-isolated floor. The missile and other critical equipment are shock-isolated. Engineering mountings are built to survive shock, and blast valves and similar equipment are made to operate through ground shock. A ground nuclear explosion forms a huge crater and may create millions of tons of debris. Surface or near-surface structures within the crater have no hope of survival. Soil and rock in the region will be severely fractured, deformed, and overlaid by tons of material. Survival is probable for a hardened Minuteman, however, even if the bomb is a near miss. Falling debris can affect Minuteman in several ways. Impacting boulders and large chunks could damage launcher closures and rails, and can destroy radio transmission by smashing antennas. Large quantities of debris could block the closure or fall into the launch tube when the closure opens prior to launch. Even if the missile survives the fall-in debris, there is the possibility that rocks at the bottom of the launch tube may be lifted by the rocket engine gases and cause damage to the weapon system. How then is Minuteman hardened and protected against cratering and debris? By three practical methods. The launcher closure is designed to open even if it is covered by debris, with debris bins that limit the amount of fall-in debris, and debris pits are built into the air ducts to absorb the rocks and rubble. Each portion of the Minuteman weapon system must be designed, built, and hardened to withstand each of the 6 primary effects of a nuclear environment. Ideally, Minuteman and its facilities should be exposed to an actual surface nuclear explosion test bomb to demonstrate survivability. Since this is not possible because of the Nuclear Test Ban Treaty, simulation testing is combined with engineering analysis to verify Minuteman protection methods. A broad selection of nuclear simulation tests are now being conducted to qualify and validate hardness of each element of the system. A full-scale facility was also constructed to test the missile shock isolation system. The missile stands on its base on the bottom of a cage structure, larger in diameter than the missile first stage. The cage is suspended by 3 cables, each terminating at a giant mechanical and liquid-type spring that provides vertical shock isolation for Minuteman. Horizontal shock isolation for Minuteman is provided by large elastic foam blocks at the upper and lower ends of the cage to inhibit impacts against the launch tube facility wall. At the top of the missile cage, 6 curved suspension units hold Minuteman centered in the cage in an upright position. Foam cushions press against the missile unit just before launch when they pivot away, leaving the missile freestanding on its base and ready to go. A major test facility was also assembled at Vandenberg Air Force Base in California for testing the full-scale shock-isolated floor from the launch equipment room that surrounds the top portion of the Minuteman launch tube and holds critical electronic equipment. This floor is suspended as it would be in an operational facility and is held by 4 liquid spring shock isolators. Horizontal shock isolation is again provided by heavy foam blocks around the edges of the floor. And vertical shock isolation is provided by the liquid spring shock isolators. Since survival of the system depends upon survival of the electronics, tests are conducted to expose the electronic racks to the kind of shock and vibration environment they would experience on the shock-isolated floor during a nuclear attack, and to establish their fragility and failure levels. The Minuteman motor generator set is also essential to missile launch and must be made to survive. Located on the launcher equipment room lower floor, next to the launch tube, the unit is a rugged 400-cycle generator integral with 2 motors mounted on rubber shock isolation blocks. Power to the unit is commercial or diesel or batteries in an emergency. And this is a shock test of those batteries. 4 high-explosive simulation technique tests, called HEST tests, were conducted to match the pressure and time of the air blast wave on a Minuteman facility located a certain distance from a nuclear explosion. Primacord was the energy source. A 300 by 300 foot room was constructed above a Minuteman facility. Numerous columns supported a roof 10 to 12 feet high and a soil layer 15 to 20 feet thick. Then, an array of wooden racks were wrapped in primacord and placed into position for the test. When everything was ready, the count began, and the primacord was detonated. Confined pressure from the explosive filled the room and had to lift the heavy soil overburden out of the way. This took time, and by tailoring the shape of the room, the amount of soil layer, and the amount of explosive, the downward pressure simulated the static overpressure and air blast-induced ground motion of a nuclear explosion. Survival of Minuteman requires that each element of the system be able to endure exposure to the total nuclear environment. Failure of any launch essential element of Minuteman because of the effects of any portion of the total nuclear environment, will make the Minuteman weapon system vulnerable and unable to complete a successful launch. Hardness is a painstaking requirement. The encouraging success of the Minuteman hardness program has led directly to the current Minuteman upgrade program. Hardness is an ongoing requirement, and it requires careful, ongoing attention. Each item of Minuteman equipment must be qualified by thorough analysis or tests, or a combination of analysis and testing to establish a go condition in the total weapon system. Minuteman validation tests are conducted on critical components to explore the degree of inherent hardness they contain above the required design level. And Minuteman demonstration tests are conducted for major subsystems, with all electronic devices turned on and operating. Minuteman is the primary weapon system that protects us. The goal of the Minuteman weapon system hardening program is to shield that system from the lethal effects of a nuclear bomb attack. Minuteman must always be ready. We don't know how advanced the enemy's technology will become. What is certain is our need to survive those advancing technological changes. This is the continuing job, the steady, consistent challenge within the Minuteman Hardness and Survival Program.